Hello all, welcome to this introductory video on image restoration. So before proceeding, let's understand what is the difference between image enhancement and image restoration. So image restoration attempts to reconstruct or recover an image that has been degraded by using a priori knowledge of the degradation phenomena. Thus, restoration techniques are oriented toward modeling the degradation and applying the inverse process in order to recover the original image. So, in enhancement, what do? We try to enhance the quality of image which should appear nice to humanize. With, that is what we try in the image enhancement. But in image restoration, what we try to do, we first try to find out the degradation phenomena. We try to find out the degradation phenomena. Then we try to model that degradation phenomena. Once we model the degradation phenomena, then we try to do the inverse of that process. Inverse of that process we do to restore the image. So the restoration part is inverse of this degradation phenomena, that is called restoration. So now hope you this is clear. The image restoration is clear. So in this, degradation phenomena is already known to the person who is trying to restore the image. Okay. So moving ahead, next we have a model of the image degradation restoration process. So here is the original image, that this is original image, and here it is passed through a degradation function. That means if we know this degradation function, then this can be treated as a function. So when it passes through this degradation function, we get here the degraded image, and in the degraded image, this some noise will be added in the processing, in the transmission, somewhere the noise will be added. So after adding this noise, this is the image which is degraded image, and that will be input for the restoration filter. This will be input for the restoration filter. Now in restoration filter, what we try to do, we try to reduce this, we try to uh, reduce this noise to zero, and we try to perform operation inverse of this degradation function in this restoration filter, and then we try to achieve an image which is same as this original image, the input image. So we will be able to retrieve this image if we know the degradation function, if we have good knowledge about the degradation function, and if we have good knowledge about the noise which has been added into the image, if we know these two, we will be very much near to the original image at the output of this restoration filter. So hope this degradation and restoration uh, process is clear from here. Now next, so this we already have discussed. Here fx is the input image, gxy is the degraded image, and this h function h is called degradation function, and this eta xy is called additive noise. So and this f cap xy is the output image, and we try that this f cap xy is as much close as this original image, and this is possible if we have knowledge about this degradation function and the noise. Okay, moving forward. Now how can we represent this in spatial domain and uh, frequency domain? So if h is a linear position invariant process, then the degraded image is given in the spatial domain by This is the degraded image gxy, that is equal to hxy convolved with the original image fxy, convolved with the original image fxy. So hxy, we can say this is the degradation function, and this is the input image. So the output of this block, output of the degradation function will be given by hxy convolved with fxy, and when we add noise in this, then we get the degraded image. So this noise is added later on, so this we get what, the degraded image. So this is how we represent in the spatial domain. So this hxy is the spatial representation of degradation function. This asterisk represents what, spatial convolution. Eta represents additive noise. Fxy represents the input image. Then if we want to represent this in frequency domain, then the frequency Fourier transform of gxy, the degraded image, is guv, and the Fourier transform of the degradation function hxy is huv. This is convolution in spatial domain. So convolution in spatial domain is multiplication in Fourier domain or frequency domain. So this is multiplied. This degradation function coefficients are multiplied the frequency representation of the input image, that is FUV. Then simply the noise NXY, its Fourier transform is eta xy, is Fourier transform is NUV. So that is added. So this is how we represent the degraded image in the frequency domain. Now, we will see some of the possible reasons by which image is degraded. So, image can be degraded during the display mode. When we send the image to the display, that time it may be degraded. Image may be degraded during the acquisition. When we acquire the image using the sensors, that time image may be degraded, and image may be degraded during the processing mode. So when we are performing some operation, that time we may lose some data, or we may misplace some data. So that time also we can uh, degrade the image. And this degradation may be due to sensor noise. Now, noise can be added due to the sensor noise. It can be added due to blur due to camera misfocus. Then relative object camera motion. If the motion of object and camera, relative motion of object and camera is uh, much, then the image will be further again degraded. Then the another reason is random atmospheric turbulence is another reason of degradation of image. So these are some of the reasons of the degradation of image. Now, next comes is the noise models. So we will discuss some of the basic noises which are used to model the noises in the image. So the first noise is Gaussian or normal noise. The probability distribution function of this Gaussian noise is given by this formula, that is equal to 1 upon under root 2 pi sigma e raised to the power minus z minus mu square divided by 2 mu square, where mu is the mean of z, sigma is standard deviation, and sigma square is the variance of this. Now, the Gaussian noise is very famous because of its shape. This is the shape of the Gaussian noise. Uh, then why it is quite famous? Because the Fourier transform of the Gaussian shape is the same Gaussian shape. So it is same in spatial domain and frequency domain. That is why Gaussian noise is very popular. Now, another property of the Gaussian noise is approximately 70% of its values will be in the range mu minus sigma to mu plus sigma. So here this is mu. At mu, its PDF is having the maximum value, and the 70% of its values will be from mu minus sigma to mu plus sigma, and 95% of its values will range in between mu minus 2 sigma to mu plus 2 sigma. So somewhere here it will be mu minus 2 sigma, and this is the mu plus 2 sigma. So in between these two we get 95% of its values. So this is the first noise, that is Gaussian noise. Then the second is Rayleigh noise. So the probability distribution of the Rayleigh noise is given by this. So it starts when z is greater than a, greater than or equal to a. It is 0 when z is less than a. Its mean is given by this formula, and its variance is given by this formula. And the distribution of Rayleigh noise is given like this. So it starts from a and it goes high, and it will be maximum at 1 plus under root b by 2, and its maximum value will be this, and then it comes down and it will be 0 again. Then this Rayleigh noise is used to approximate the skewed histograms of the image. Now you see this Rayleigh noise is little bit skewed in the right hand side. Here it has been skewed. So if we want to approximate the skewed histograms of the image, then we can use Rayleigh noise to approximate those histograms. Then next we have airline or gamma noise. So probability distribution function of this is given by this formula, and its mean is b by a, its variance is b by a square, and its shape is given like this. It is maximum at b minus 1 by a, and its maximum value is k, and k is given by this one. The another common noise is exponential noise. So exponential noise is given a e raised to the power minus az when z is greater than 0, and 0 when z is less than 0. So its mean is 1 by a, and its variance is 1 by a square. And if we plot this curve, then we get this. At z is equal to 0, it is going to be a, and then as z increases, this increases. So this decreases. So this decreases exponentially like this. So this is exponential noise. Then next comes is the uniform noise. Probability distribution of the uniform noise is given by this. Here it is defined only between A to B, only in the range of Z from A to B. From A to B, it is a constant, that is 1 upon B minus A, and otherwise it is 0. Otherwise it is 0. And its mean is A plus B by 2, and its variance is my b minus a square by 12, right? So this is how we have the plot of probability distribution function of uniform noise. It is from a to b, it is constant 1 upon b minus a, and for remaining values of z it is 0. The next quite important noise, that is impulse or salt and pepper noise. Probability distribution of this is given by, it is pa, its probability is PA for z is equal to A, and it is PB for z is equal to B. That means it will be defined only for two instances of the random variable z, right? It will be defined only for two instances, that are A and B. Otherwise, it will be 0. So its probability distribution is like this. At when z is equal to a, its probability is pa. When z is equal to b, its probability of occurrence is pb. Now if b is greater than a, b is greater than a. Now since we know that salt and pepper noise will have a dots, black and white dots. So if b is greater than a, then gray level b will appear as white dot in the image, and the A will appear as black dot in the image. And if either of P and PB is 0, then impulse noise is called unipolar noise. So if either of these two is 0, that means only one type of dot will be appear, either black dot or white dot will appear. So that is why it is called unipolar noise in that particular case. I hope this is clear. That's it for this lecture. Thank you for watching.